Good morning all. In today's class, let us discuss about binding energy curve, liquid drop model, shell model and magic numbers. First, what is mass defect? So, the mass of stable nucleus is always less than masses of constituent nucleons. Means here theoretically, if we calculate the mass by using the formula ZMP plus A minus Z of Mn, we will get certain value where Z is the number of protons, MP mass of protons, A mass number, okay, Mn number of neutrons, right? By using this formula, if we find the mass, we will get certain value. Now next, experimentally, if we find the value, that value will be other than this theoretical value, the calculated value. Now the difference between the real mass and this calculated mass, we call it as mass defect. The difference between sum of masses of nucleons and rest mass of nucleus, we call it as mass defect. So now the mass defect, it is written as ZMP plus A minus ZMn minus M. Okay. Next, binding energy. The energy required to split the nucleons or the energy required to bind the nucleons, we call it as binding energy. Now next, let us move for this binding energy curve. This curve is drawn by taking mass number on x-axis, binding energy per nucleons on y-axis, right? Now for each and every atom, we draw this curve. Now see the curve. Okay. Now in such a way, the curve is there. Now let us discuss some important facts which this curve is showing. The first point is that where the curve is becoming maximum, at some mass number 50, curve attains the maximum binding energy value. That maximum binding energy value is 8.8 million electron volt. For that particular atom whose mass number is equal to 50, that atom will get the maximum binding energy of some 8.8 million electron volt. Okay. Now after A equal to 50, it is again starting decreasing. Here it became maximum. At iron, it became maximum. And again it starts decreasing. Okay. So, if first it decreases to 8.4, right? 8.4 after A equal to 50. Now at nearly A equal to mass number 140, it decreases to more value, okay, and at nearly for uranium mass number 238, it decreases to 7.6. It decreases to 7.6 million electron volts. So here it is giving the binding energy values. So binding energy maximum value is 8.8 million electron volt. As mass number goes on increasing, the binding energy decreases, and at nearly uranium 238, it becomes 7.6 million electron volt. Right? So as mass number increases, binding energy decreases, and the maximum binding energy, that is 8.8 million electron volt, we will get for iron. Okay. Now next, the second point which we know is that, so the maximum, that particular elements whose mass number is or ranges between 30 to 170, the particular elements whose mass number ranges between 30 to 170, they have binding energy closer to the maximum binding energy value. How their binding energy will be? Closer to the binding energy or maximum binding energy value for the elements whose mass number ranges between 30 to 170. Their binding energy will be closer to the maximum binding energy value, that is 8.8. Means they will have 8.4, 8.2. In such a way, their binding energy will be closer to the maximum binding energy value. Next, now here you see the curve. This is lithium, this is helium, lithium. Okay. Now next, in such a way, carbon, oxygen, nitrogen. Okay. In such a way, you see, for some elements binding energy is increasing, for some elements binding energy is decreasing, again increasing, again decreasing, increasing, decreasing, and at last it became 8.8 million electron volt. Now let us talk about this particular area. Now what is happening here? Now if we take helium, He24, if we take carbon, C612, in such a way, what we are finding? We are finding maximum binding energy compared to the nearby atom, compared to nearby or neighboring element. Right? So for helium, neighboring element is lithium. Compared to lithium, helium is having more binding energy. Now compared to helium, carbon is having more binding energy, and compared to, after carbon we will get nitrogen. Compared to nitrogen, carbon is having more binding energy. Right? So now here, and next, if we see lithium, nitrogen, etc., these are having less binding energy compared to the neighboring elements such as helium, carbon. Compared to these neighboring elements, they are having less binding energy. So what this shows means, what this particular thing is saying means, here binding energy is maximum for helium, carbon, etc. we said no. So here if we observe this atomic number and number of neutrons are same. atomic number is 2. Sorry, Z. Atomic number is 2. And the number of neutrons, A minus Z, 4 minus 2, 2. So number of neutrons is equal to number of protons. Means binding energy is maximum for that elements in which number of neutrons is equal to number of protons. Right? And now next, another thing, these nuclei with here 2, 6, next 8, in such a way, even proton numbers are more stable compared to the nuclei with odd proton number. So nuclei with even proton numbers are more stable compared to the nuclei of odd proton number. Alright. Now if we talk about physical significance, the physical significance, it determines stability of nucleus. What this binding energy curve gives, it determines stability of nucleus. This curve says that nucleus emits large amount of energy when it disintegrates into constituent particles. Disintegrating into constituent particles means uranium breaks into barium and krypton. Uranium, while bombarding with a neutron, breaks into barium and krypton, means it breaks into constituent particles. When it is breaked into constituent particles, it emits large amounts of energy. So this process we call it as nuclear fission process. We call it as nuclear fission process. Similarly, when two nucleus fuse with each other, such as hydrogen, proton plus proton, when they fuse each other also, a large amount of energy is released. Now this process we call it as nuclear fusion process. Okay. So this is the physical significance of binding energy curve. Now next, let us go for semi-empirical mass formula. So in 1935, von Weizsäcker, scientist, he said that this mass number formula can be written in terms of binding energy. Okay, this mass number formula can be written in terms of binding energy terms, binding energy correction terms. So now the mass number, the change in mass of a nucleus, it is written as mZa equal to Z mp plus n mn minus b, where b is nothing but binding energy. And how to calculate the binding energy? The value of binding energy is equal to EV plus ES plus EC plus ER plus EP. Now let us see what are these terms. First, EV. EV we call it as volume energy correction. Volume energy correction. Okay. So now here, this is nucleus. Nucleus consists of number of protons and neutrons binded with each other. Now this is the entire volume of a nucleus. The energy over the entire volume of nucleus, the distribution of energy over the entire volume of nucleus is constant. So the total binding energy will be directly proportional to the number of nucleons present in the nucleus. So binding energy means what? Either binding of nucleons or splitting of nucleons we said. So binding energy is directly proportional to the number of nucleons. So number of nucleons means nothing but the mass number. EV proportional to A, where EV equal to AV, AV we call it as proportionality constant. So this is the formula for volume energy correction, AVA. Now next one, let us go for ES. ES means surface energy, right? So now here, as we see, if we compare this nucleus with general atomic structure, how will be the general atomic structure? Nucleus will be at the center. These all are the different shells. We call K, L, M, so on. So electrons will be filled up in these particular shells, right? Now this last shell, we call it as outermost orbit. And the electrons lying in this outermost orbit are loosely bounded to the nucleus, right? The electrons in outermost orbit are loosely bounded to the nucleus. In a similar way, even the nucleus is having nucleons, protons and neutrons. So some nucleons will be on surface of nucleus. So that nucleons which reside on the surface of nucleus which are on surface of nucleus are loosely bounded, okay, are loosely bounded. So as these nucleons which are near the surface of the nucleus are loosely bounded, there will be slight reduction in binding energy. So the total binding energy is taken in negative terms. Why we are taking in negative terms? Because as the nucleons residing near this surface of nucleus are less tightly bounded, there will be slight reduction or decrease in binding energy. Alright? So binding energy is taken with a negative term due to reduction in binding energy. So now the number of nucleons will be equal to the surface area 4 pi r square. So or we can say r square. Number of nucleons on the surface of nucleus is proportional to the surface area 4 pi r square. So number of nucleons we can write proportional to r square. But we know that r is equal to r naught a to the power of 1 by 3, right? The radius of nucleus. So number of nucleons is proportional to r naught a to the power of 1 by 3 whole square. Or we can also write it as number of nucleons proportional to a to the power of 2 by 3. Right? Number of nucleons proportional to a to the power of 2 by 3. As there is reduction in binding energy, we will write it as ES is equal to minus AS a to the power of 2 by 3. So this is the value for surface energy correction. Alright. So now next, let us go for EC. EC means Coulomb energy. So as we know, nucleus consists of protons. So 100% there will be force of repulsion, electrostatic or Coulombic repulsive forces between these protons in the nucleus. Due to that repulsive forces, again the binding energy decreases. As binding energy is decreasing, we take again energy in terms of negative terms. So Coulombic repulsion energy of binding energy is EC equal to minus AC Z minus 1 by a to the power of 1 by 3. Now next, let us move for ER. So ER means asymmetry energy. Actually, for n equal to Z only, the nucleus will be more stable compared to other nucleus. In the nucleus, where the proton number is equal to the neutron number, that nucleus will be more stable compared to the neighboring nucleus. So this effect we call it as symmetry effect. But as mass number increases, neutron number increases. So when neutron number increases, alternately binding energy decreases. Now this decrement of binding energy due to the increase in mass number, thereby increase in neutron number, we call it as asymmetric energy correction. The decrease in binding energy due to increase in mass number, thereby increase in neutron number, we call it as asymmetric energy correction. If Z is the atomic number, A is the mass number, then there will be Z protons, A minus Z neutrons, right? So if excess neutrons are present, then how we will write? So the excess neutrons over protons is written as A minus Z, that is equal to A minus 2Z, right? Here also, as there is reduction in binding energy, the expression is taken in negative terms. So ER equal to minus AR, A minus 2Z whole square by A. Now next, pairing energy. So here it indicates about the stability of nucleus. If number of protons and number of neutrons are in even number, that nuclei will be more stable, right? If number of protons or number of neutrons, any one is odd, here proton number is odd, neutron is even, here proton is even, neutron is odd. In these two cases, if either Z or N, any one is odd, then we will have intermediate stability for nucleus. And if both are odd, Z as well as N, both are having odd numbers, that nucleus will be least stable. So this is about pairing energy, and the value will be EP equal to AP a to the power of minus 2 by 3. Okay. So now if we add all this and substitute in this formula in the place of B, we will get the complete mass of a neutral atom expressed in binding energy correction terms. Okay, binding energy correction terms. Now next, let us move for liquid drop model. So in liquid drop model, it is explained by Bohr. He says that nucleus can be assumed as a small electrically charged liquid drop. Nucleus can be assumed as a small electrically charged liquid drop. So only it takes a spherical shape, and it takes a spherical shape for stability itself only. Okay, it takes a spherical shape for its stability itself only. So now he compared this total nucleus with liquid drop. Now in liquid drop, how these molecules will move within the enclosure of that drop, the nucleons, that is protons and neutrons, will move within the spherical enclosure of a nucleus, will move within the spherical enclosure of a nucleus. Here also, as we are having intermolecular distance, there will be a nucleons also are having a particular distance between them. Nucleon will have a distance between them, and like molecules only, they share the energy, the complete energy of the nucleus. They share the complete or total energy of the nucleus. So each nucleon inside the nucleus interacts strongly with the neighbors. Okay, so here as a liquid drop, this is the nucleus, protons and neutrons are there, nucleons are present. So these nucleons interact strongly with the neighbors. Already we saw, no, neutron, proton, proton, neutron interactions. So in such a way they interact strongly with their neighbors. So inside the binding energy will be more. But what happens at a surface area of nucleus? Already we discussed, no. So in surface area, the nucleons which are present on the surface area of nucleus, they are less tightly bounded. As they are less tightly bounded, binding energy will be less. But inside they are tightly bounded. So binding energy will be more inside the nucleus, and there will be a slight reduction in binding energy at the surface of a nucleus. Okay. Now just board he gave some similarities between liquid drop and our nucleus. So the attractive forces in nuclear surface he compared with the surface tension. The attractive forces near nuclear surface he compared with the surface tension. Now in both cases, either in the molecules of liquid drop or the nucleons of nucleus, the density of nuclear matter is independent of the volume. In both cases, the density of matter is independent of the volume. Right? Now next, as molecules vibrate about their mean positions, nucleons also vibrate, okay, or move about mean position. Nucleons also move about the mean position and interact with the neighbors, as in molecules it happens. Okay. Now next, the next similarity is the constant binding energy per nucleon. He compared with latent heat of vaporization. Okay, what is latent heat of vaporization? So that particular heat required to convert a liquid into steam or vapor, that we call it as latent heat of vaporization. So now here binding energy per nucleon is equivalent to the latent heat of vaporization. Right? Now next, here the disintegration of nucleus. Disintegration of nucleus means here nucleus converts into the lighter nucleus by the emission of alpha beta radiations. Right? So that we call it as disintegration of nucleus. So here he just compared this disintegration of nucleus with evaporation of molecules from liquid drop, surface of liquid drop. So if you continuously boil water, what happens? After 1 hour or 2 hours, if you see, you will not find water in the bowl. Why? Because it is evaporated. It has converted into the gaseous state from liquid state. Similarly, in such a way, he compared this evaporation of molecules from surface of liquid drop with disintegration of nucleus. What is disintegration? The emission of alpha beta particles converts the heavier nuclei into the lighter nuclei. Right? Now next, the internal energy he compared with heat energy of the molecules. Okay? Now next, here the nucleus, when bombarded with some bombarding particles, it absorbs that bombarding particles and forms into compound nucleus. And this property they compared with condensation of vapor to the liquid. So especially in the winter seasons, you will see the water droplets on leaves. What is that? Condensation. Condensation of vapor into the liquid. So he compared the capturing of bombarding particles and forming into compound nucleus. He compared it with the condensation of vapor to the liquid. And for stability, as the molecule, the nucleus also will have spherical shape. Okay. Now this is about liquid drop model. Alright. Now next, let us move for magic numbers. What are magic numbers? So before going for magic numbers, first let us compare the atomic structure and nucleus structure. How the atomic structure will be? In between nucleus will be there. Orbits are there. In these orbits only electrons will revolve. Okay. These orbits are named as K, L, M, so on, shells. These are named as shells. K, L, M, so on, shells. Similarly, nucleus, it consists of protons and neutrons. Okay. Circle you think as a proton, the solid circle as neutron. Then 100% there will be a distribution in this proton and neutron. No? Same like atomic structure, how these electrons are distributed in these shells, in nucleus also, these nucleons are distributed in shells. To indicate that only, we got shell model. Shell model of nucleus. We got shell model. Right? This is the first thing why we are talking about the shell model of nucleus. Now the second thing about magic numbers. So now here, if we take some we call inert gases, no? What are inert gases? Helium, neon, argon, radon, so on. Inert gases. So, what is happening in the inert gases? Why we call it as inert? Because if we take the example of helium, so what happens? Nucleus. In outermost orbit, the electrons are completely filled. If we take neon, 2, 8 electrons in outermost orbit. So outermost orbit requires 8 electrons, and 8 electrons are present in outermost orbit. So it is chemically inert. Means it will not participate in a chemical reaction, because here there will be no acception of electrons or giving or donating of electrons. So these particular atoms cannot participate in chemical reactions only due to the reason that their outermost orbits are completely filled. Alright. So now we want to remove an electron from this outermost orbit. Then we have to apply some large quantity of energy to remove the electron from outermost orbit. We require large quantity of energy to remove the electron from the outermost orbit of such inert gases. Right? In a same way, even in the nucleus, if we see, to separate the nucleons, we require large amount of energies. To separate the nucleons, we require large amount of energies. Okay. So now here energy is taken in form of electron volt, and here it requires more energy than this electron volt. That is, here we write it as million electron volt. Okay, here we will write it as million electron volts of energy is required to remove a nucleon from the nucleus. Right? Now next, here the third point. So in the third point, here what we are saying, in inert gases, as outermost orbit is completely filled with this electrons, this is stable. Right? Similarly, not only these inert gas atoms, but also some other atoms are there. Some other atoms are there for which the nucleus will be stable. Nucleus is stable. Not only these inert gases, atoms, but there are some other. It is found that some other atoms with particular numbers, will have nuclear stability, or their nucleus will be stable. So that numbers we call it as magic numbers. That numbers we call it as magic numbers. I think you understood what are magic numbers. So other than these inert gases, some atoms or elements are there with particular numbers. So at that particular, if they have that particular number, that particular element will have nuclear stability. Nucleus will be stable for that particular element. So that numbers for which nucleus will be stable, we call it as magic numbers. Now this is the basic explanation for magic number and shell model. Similarly, how we are having the shells and how electrons are distributed in the shells, similarly the nucleons are distributed, and this distribution totally depends upon Pauli exclusion principle itself only. That nucleons which are having opposite spin can stay in one shell. Okay, this distribution of nucleons totally depends upon Pauli exclusion principle itself only. Okay, so now let us move forward. Now this is about shell model. The main importance of shell model is it gave the experimental evidence of existence of magic numbers. The significance or importance of shell model is it gave existence of the evidence for existence of magic numbers. Alright, now let us move for that magic numbers. Alright, so now what are that magic numbers where we are finding nuclei stable? That magic numbers are 2, 8, 20, 28, 50, 82, 126. These we call it as magic number. So the particular nuclei having these number will behave in different manner than their neighboring nuclei. Either this number will be for Z, or either this number will be for N, or either this number will be for both Z and N. Either atomic number may be a magic number, either number of neutrons will be a magic number, or atomic number as well as neutron number both will be magic number. Then the behavior of the nuclei with such magic numbers will be different from the neighboring values. The nuclei having neighboring values of Z and N. Okay. Now let us go for the experimental evidences, the existing of magic numbers. First, the binding energy for magic number nuclei is larger compared to the binding energy of neighboring nuclei. Okay, so large energy is required to separate a single nucleon. Now only in shell model explanation I said no, it required nearly million electron volt energy to separate a nucleon. Alright, so now if Z and N atomic number, neutron number, both are magic numbers, then they will have a number of isotopes. Such a nuclei will have number of isotopes. For example, if we take calcium 2040, atomic number is a magic number, right? Magic number, in magic numbers we are having 20, and a number of neutrons 40 minus 20, that is 20. So Z is magic number, N is magic number, it has nearly 6 stable isotopes. And for tin also, Z is magic number, N is magic number, it has nearly 10 stable isotopes. Right? Now next, in some cases, either Z or N, anyone will be magic number. Now such we find plenty in nature. We get they have greater relative abundances. So we will find it plenty in nature. Such as example, if we take this strontium 88. Okay. So here number of neutrons is magic number. Okay. Now here if we take barium, here also number of neutrons is a magic number. Atomic number is not magic number. So they find abundant in nature. Now next, we already know that above 83 bismuth, these elements emits alpha beta radiations and disintegrate into lighter nuclei. So there occurs this radioactive series such as thorium series, uranium series, okay, radioactive series. Now in this radioactive series, if we see uranium, it disintegrates into thorium, thorium again disintegrate. In such a way they go on disintegrating and at last, the last element we will get lead. Thorium, uranium. So in such a radioactive series, last we will get the stable element lead. These three particular radioactive series, at last they disintegrate to gain stability only, and the last element, that is we will get lead 82. After continuous disintegrations, we will get the stable element 82. Now here you see Z 82, it is a magic number. N 126, it is also a magic number. So only lead nuclei is more stable. Here both are magic numbers. E is more stable. Next, if neutron absorbing cross section is very low, for the nuclei having neutron number as magic number, if neutrons are having magic number, then neutron absorbing capacity will be very low for that particular nuclei. Next, nuclei with magic numbers of neutrons or protons have their first excited states at higher energies only. Means they will excite to very higher energies than in the case of neighboring nuclei without magic numbers. Right? And next, electric quadrupole movement will be 0 for the magic numbers. Okay? So only they get a spherical symmetry and nucleus will be nearly spherical in nature. Now next, energy of alpha beta particle emitted by magic number radioactive nuclei is larger from other nuclei. Now here if we take the example of, so any radioactive element, either Z or N or both are magic number and it is emitting alpha beta particles, then that radioactive material, that radioactive nuclei with magic number will emit larger amount of energies compared to the other nuclei without magic numbers. Right? Now we will have doubly magic numbers. Doubly magic numbers means if we take Z and N, both are magic numbers. Helium 2,4, Z is 2, N is 2. Oxygen 8,16, Z is 8, N is 8. Magic number. Calcium 20,40, Z is 20, N is 20. Lead 82,208, Z is 82, N is 126. These all are magic numbers. So these are more stable. Okay. Now next, single magic numbers. Single magic numbers means either N or Z. Any one will be magic number. Now if we take strontium 3888, Z, it is not a magic number. But N 50 we got, it is magic number. Right? Now next, semi-magic numbers. So here other numbers of Z or N at which binding energy per nucleon is high, then but in other properties the evidence of special stability of nuclei are less marked than that of the magic number. So it says that either Z or N, if it is a magic number and for which binding energy per nucleon is more, it will have a special stability of nuclei compared to that nuclei without magic number. So this is about magic number. So what is magic number here? We are saying either Z or N. Any one must be a magic number, and if binding energy per nucleon is more for that, then that particular nuclei will have special stability compared to the other without magic number. So totally what are magic numbers? Magic numbers are 2, 8, 20, 28, 50, 82, 126. So with these numbers, either Z will be magic number or N will be, or both will be magic number. Anything may happen. Depending upon that only their properties will change. So for this, nuclear stability will be there compared to other nuclei. Okay. And they have some special different properties and they behave differently compared to the neighboring nuclei. So these numbers we call it as magic numbers. Thank you. If you like this video, like it, share it, subscribe it. Thank you.